This is Earth, and this is Earth. This is Earth, and this is also Earth. Over billions of years, our planet has changed significantly, and it will continue to change. It hasn't always been and won't always be this kind of oasis in space. It was once covered by a molten ocean of lava and will likely become a hot, dry desert, and may have even been a frozen ball of ice at some point. Imagine ice fields stretching for thousands, even tens of thousands of kilometers, even in the tropics, even at the equator. We've all heard of ice ages, but this is on an entirely different scale. There is a hypothesis called Snowball Earth, according to which there were periods in the past when all or nearly all of the planet's surface was covered in ice. Temperatures, even in the tropics, could have dropped to -50 degrees Celsius or -58 Fahrenheit. At that time, the planet would have looked more like Enceladus. But I said it's a hypothesis. Some scientists hold this view, and there are quite a few arguments in favor of this idea. At the same time, there are also many opponents of this hypothesis. What are the arguments for it? How could the entire planet freeze over? Why didn't this kill all life? If this really happened, and even more than once, as some scientists believe, how did our planet manage to break free from this state? And could it happen again? We'll talk about all this today and more. I'm Andrei, and this is Cosmos Elementary. The idea that the entire planet could be covered in an icy crust sounds like a plot for some disaster movie. But what is so strange and controversial about this that scientists still debate whether it happened or if the entire Earth froze completely or just parts of it? The climate on Earth has noticeably cooled several times during periods broadly referred to as ice ages. That we know for sure. But for the entire ocean to freeze, for equatorial regions, which typically have a consistently high temperature throughout the year and experience minimal seasonal variation, to also freeze, that does sound truly anomalous, especially when temperatures could drop to -50 degrees Celsius, as in the most extreme scenarios. It is hard to imagine what could have caused this and how Earth could have gotten out of such a state. So, according to this hypothesis, a long time ago, back in the Precambrian, specifically during the Neoproterozoic era, a global glaciation could have occurred, and possibly more than once. During the period from approximately 720 million to 660 million years ago, the so-called Sturtian glaciation may have occurred. Then followed the shorter Marinoan glaciation, which may have begun around 645 million years ago and lasted several million years. It's also suggested that there might have been a third glaciation episode slightly later, but it was even shorter. All of this occurred during the Neoproterozoic period, which is also known as Cryogenian. You don't need to guess why. By the way, there's also talks of a possible global glaciation over 2 billion years ago, but today we're focusing on Cryogenian. There's more evidence for it. But why do some scientists even think that Earth could have been in a snowball state for many million years? In short,
yes. Geology.
A little less briefly, geologists find certain types of deposits all over the Earth that have or may have glacial origins. This in turn may indicate that this area was once covered by ice, and such glacial traces are even found in the tropics. So, if the tropics were covered in ice, then the rest of the Earth must have been covered in ice as well at that time. A careful viewer might start to have some questions. For example, we're talking about the Neoproterozoic, a period 700 to 600 million years ago. If we find glacial deposits in modern tropics, what makes us think that this landmass was in the tropics back then? We now know that tectonic plates do not remain stationary. The appearance of the Earth's landmasses is constantly changing. The current continents were once part of a supercontinent Pangaea, which existed 300 to 200 million years ago. So the time we are talking about today was even long before Pangaea. Other supercontinents existed then. In general, we need to find glacial traces, confirm that they are indeed glacial in nature, and also confirm the time of their formation, and also determine at which latitudes this landmass was located at the time those deposits were created, hundreds of millions of years ago. This sounds more complicated already. Although the name of the hypothesis, Snowball Earth, is relatively young and first appeared in the 90s, hints that the Earth could have completely frozen in the past had been found by scientists long before that. Deposits associated with glaciers, including in tropical regions, were found as early as the 19th century. Although, at that time, it was believed that the continents were stationary. By the way, I discussed continental drift and plate tectonics in more detail in my video about the expanding Earth hypothesis. In the context of a more modern view of our planet, in 1964, Brian Harland was one of the first to find evidence that glaciations occurred at tropical latitudes. He analyzed glacial geological formations in Greenland and Spitsbergen, which were dated to a period when these areas were in the tropics. We'll talk more about how dating was done later. In 1969, Soviet climatologist and geophysicist Mikhail Budyko developed a climate model that he called the ice catastrophe. In this model, the polar caps extended so far from the poles that ultimately the entire Earth froze. Budyko himself did not consider such a scenario to be possible and did not examine how the Earth could emerge from it. The term Snowball Earth was coined by Joseph KIRSCHIVINK, who used it in his 1992 paper. One of the most well-known proponents of the Snowball Earth hypothesis is Paul Hoffman, who has dedicated decades of his scientific career to this topic. Let's now delve deeper into what kind of evidence scientists have found. The problem with finding evidence that there was ice in a currently warm region is that, well, ice melts. However, traces that ice leaves on various rocks are well preserved, and we can find them. Geologists looking at the layers say there was a glacier here. And let's play a game. I'm something of a geologist myself. I will show you photographs of rocks. For example, here. Try to guess what indicates the influence of ancient glaciers. Here's another example. If you want, you can pause the video and write your thoughts in the comments. And here is the answer. Surely many of you have figured out that it's all about those parallel lines. Glaciers on land typically do not just sit in place. They slowly move. Between the layer of ice and the bedrock beneath it, there can be stones and small particles of various sizes. And the mass of ice, while moving, drags these stones and particles along, leaving grooves in the direction of the ice movement. So, if we find such grooves, it can indicate that there was once a glacier here. Another example is teolite. This type of rock represents a matrix, meaning a more homogeneous rock, and within this matrix we see a variety of poorly sorted stones of different sizes. You can find many images of such rocks on the internet, but in one of the articles I used as a source, there are also examples of high-resolution panoramas and even three-dimensional interactive models of these deposits. You can rotate them and examine the details. And again, the question is, what do glaciers have to do with this? So a glacier moving across the land gradually collects stones of various sizes along the way, mixing them together. When the glacier melts, for example, these materials are deposited in the soft substrate, which then solidifies into rock. It should be noted that not every rock of this type necessarily has a glacial origin. A more general term for such rocks is boulder clay. In addition to glaciers, landslides and debris flows can also transport and mix stones and rock fragments. However, it is still believed that glaciers are most often responsible, and in many cases, it is possible to distinguish these rocks as having a glacial origin. There are also things with a cool name, dropstone. Again, the inclusions of stones in the rock that look like they fell from above and then solidified. Hence the name dropstone. The idea is that when a glacier reaches the shore, it enters the sea. Just like in previous cases, as the glacier moved across the land, it picked up stones. Once in water, icebergs break off from the glacier, melt, and then the stones from them fall onto the soft seabed. which then hardens, trapping these stones. Here, besides glaciers, there aren't really any other mechanisms at play. Dropstones can vary in size, ranging from large to microscopic. Another interesting type of deposit that may indirectly indicate that Earth completely froze in the past is banded iron formations. They form in the oceans, and this is what they look like. They consist of alternating layers containing iron compounds, and layers of shale rock that are low in iron. It is believed that such deposits primarily formed a long time ago, during the period of 3 to 2 billion years ago. The thing is, back then the atmosphere and oceans were still low in oxygen. This means that iron did not oxidize, allowing for the formation of the minerals that make up these deposits. Nowadays, when our atmosphere and oceans are rich in oxygen, it is believed that these deposits do not form, so they are sometimes referred to as extinct. However, geologists find such deposits that date back to the Cryogenian period, which we are discussing today. This means that something may have happened at the time that caused the ocean to suddenly become depleted of oxygen. And such an event could be global glaciation. If ice prevents the atmosphere and ocean from interacting, the dissolved oxygen that was in the ocean before glaciation is gradually consumed in various chemical reactions. Deep-sea black smokers or hydrothermal vents could have enriched the ocean with iron again. This, in turn, created conditions for banded iron formations to form once more for a period of time. And here's one more thing. There are several types of deposits that are associated with glaciers. However, often thick layers of the so-called cap carbonates, consisting of limestones and dolomites, lie on top of them. The thing is, such minerals form well in a warm climate. Their presence and the sharp boundary between the layers can indicate a sudden warming. Moreover, these cap carbonates are found on top of glacial deposits all over the world. However, they alone do not necessarily confirm the hypothesis of global glaciation, but overall, I believe the logic is starting to take shape. Scientists find traces of glaciers scattered all over the world, corresponding to roughly this same era. There are also signs indicating the end of this era. All of this can be explained by periods when the entire planet turned into a frozen sphere. All of this is clearly wonderful, but it heavily depends on how accurately we have measured the location and time of formation of those deposits. I've already said several times that traces of glaciers are found all over the planet, but we also know that if we find deposits in today's tropics, it doesn't mean that they were located in tropics hundreds of millions of years ago. Back then, the Earth looked completely different, and the deposits we find now were located at entirely different latitudes. So we also need to find a way to determine where these deposits formed during the Neoproterozoic. One of the main methods used here is paleomagnetism. The core inside our planet generates a powerful magnetic field. It's very important for life on Earth. This is one of the protective mechanisms of our planet. Without it, at the very least, Earth could lose its atmosphere due to the impact of solar wind. But the magnetic field also helps us study our planet. Magnetic studies help confirm the theory of plate tectonics, and they're also used as one of the main pieces of evidence supporting the Snowball Earth hypothesis. The magnetic field is generated in the depths of the planet, but it extends far beyond its surface. The shape of the magnetic field can be roughly described as a torus. The lines of the magnetic field emerge almost vertically from the magnetic poles and are roughly horizontal relative to the Earth's surface at the equator. What does this give us? Just as a compass needle aligns itself along the magnetic field lines, various minerals like magnetites, which are influenced by the magnetic field, will align along these lines as well. They can do this while they are still free to move in molten lava flows or in sediment that has not yet solidified. When the material cools, crystallizes or solidifies, the magnetic minerals remain in the position they were in at that moment. Thus, they essentially record information about the state of the magnetic field at that time and about the location of the deposits relative to the magnetic field. In simple terms, the more vertically the particles are oriented, the closer they are to the magnetic pole. Conversely, the more horizontal they are, the closer they are to the equator. Geologists take samples, measure their magnetic properties, and can thereby approximate where they originated. This allows us to determine paleolatitude but not longitude. However, since we need to understand whether glacial deposits were in the tropics, latitude alone is enough. This is how it was determined that geological traces of glaciations could have formed very close to the equator. It's worth noting that it's not all straightforward here. We know very well that Earth's magnetic field does not remain constant. Currently, the magnetic poles do not perfectly align with the geographical poles. Additionally, we observe how they migrate over time. It is also believed that from time to time there are reversals of the Earth's magnetic field, when the northern and southern magnetic poles switch places. Though this does not render the method I described useless. If the poles switch places, it will still be possible to determine latitude in this way. The process of reversal can happen relatively quickly, over a few thousand years, while the interval between reversals can last hundreds of thousands or even millions of years. So, unless something very unusual occurs, it will generally be possible to determine latitude for most of that time. However, one cannot completely dismiss the possibility that hundreds of millions of years ago the magnetic field had different properties. It might not have had just two main poles but instead had more, or it could have been oriented differently. Moreover, the magnetic signal created during the formation of rocks could later be overlaid by contaminating signals. In general, while paleomagnetism is a widely used method, we cannot claim it to be 100% accurate. The second important question after location is time. How do we know that all these glacial deposits formed during the specific period and approximately simultaneously? There are different dating methods. To determine the age of a specific sample, one can use one of these methods or a combination of them. There are three main approaches. First, there is relative dating. Geological layers are deposited in order, and if we simplify it, the layer that is deeper is older, while the one that is higher is younger. Relative dating by itself may not provide specific dates, but it helps determine how a particular sample is positioned relative to other layers. For certain types of deposits, we can obtain specific numerical dates. By using radiometric dating methods, we can determine the age of a sample. I have mentioned how it works before, but knowing the half-life of certain isotopes and measuring the ratios of isotopes and decay products in the sample, we can determine its age. For example, if we have a stratigraphic section with a layer of volcanic ash at the bottom, we can determine its age using radiometric dating, and it is, say, 800 million years old. If our glacial deposits are above, then they are younger and may correspond to the period of proposed global glaciation. The third approach, already mentioned earlier, is magnetism. Studying changes in properties of the magnetic field in samples from different eras can also give us insights into timing. This is of course just a general overview. Yes, each individual argument does not prove that the Earth was 100% covered in ice at some point. However, the combination of factors, various deposits, their distribution around the world, and most importantly the tropical regions, along with their dating, compel scientists to seriously consider the hypothesis of global glaciation in one form or another. But still, how exactly could this happen? What could cause the entire planet to freeze over, covering the oceans with a layer of ice? Of course, the climate on the planet is a complex thing and depends on many factors. For the climate to change so radically, something significant must have happened. In the case of global glaciation, there are some ideas that are somewhat more extravagant. For example, as Earth, along with the entire solar system, moves through the galaxy, it could enter a dense galactic cloud. Charged cosmic particles could damage the ozone layer, while cosmic dust would accumulate in the atmosphere, resulting in a cooling effect. However, there is little evidence to support this hypothesis. Although, if scientists find an anomalous concentration of uranium-235, which does not naturally occur on Earth and is produced in supernovae, it could indirectly indicate passage through such a cloud. Still, the main hypothesis today is different. Greenhouse gases significantly influence the planet's temperature. We are currently experiencing this if you know what I mean. Greenhouse gases allow sunlight in the visible spectrum to pass through, warming the Earth. The Earth then emits heat in the form of infrared radiation, but some of this radiation is absorbed and re-emitted by greenhouse gases. In short, they trap heat. Currently, we frequently discuss greenhouse gases in the context of global warming caused by increased levels of these gases. However, the opposite process can also occur. If the levels of greenhouse gases decrease, the temperature on the planet could begin to drop. One of the main greenhouse gases is carbon dioxide. Its levels in the atmosphere are regulated by a series of processes collectively known as the carbon cycle. The amount of CO2 in the atmosphere can increase due to the volcanic activity, for example, while it can decrease as a result of chemical reactions that remove CO2 from the atmosphere when solid deposits are formed. It is believed that such processes for removing carbon dioxide are more effective in warm, humid climate. In the late Proterozoic, the land could have formed a supercontinent called Rodinia. It was presumably located in equatorial latitudes, meaning that the climate was warm and CO2 could be effectively removed from the atmosphere. Then the supercontinent broke apart, exposing more coastlines, thereby making this process even more effective. All of this could have caused temperature decrease. But that's not all. We know that the sun's luminosity is gradually increasing. This means that in the past, it was lower. In other words, the sun shone a bit less brightly, and the temperature was lower. At that time, this could have been offset by a higher methane content, another effective greenhouse gas. However, this was in an atmosphere with lower oxygen levels. As oxygen levels began to rise, methane content could have started to decrease instead. Overall, the positioning and breakup of the supercontinent, along with the reduction of greenhouse gases, could have worked in such a way that even volcanoes couldn't compensate for the drop in CO2 levels, and the climate kept getting cooler. This in turn led to the growth of polar ice caps. They started extending farther from the poles and closer to the equator, and this created a new problem in itself. Snow and ice reflect sunlight back into space much more effectively, the more the planet's albedo, or its reflectivity, grew. So it creates a chain reaction. Fewer greenhouse gases make it colder, colder temperature lead to more ice means less warming from the sun, and it gets even colder. Ultimately, this could have led to the ice reaching the equator, covering the entire planet. As I mentioned, in the most extreme scenarios, the entire ocean could have been covered with ice, and the temperatures could have reached -50°C or -58°F across the entire planet. And during the longer Stortian glaciation, the Earth remained in such a state for tens of millions of years. How did the Earth manage to get out of such a state? As the Earth was freezing and becoming increasingly covered in ice, the processes that remove CO2 from the atmosphere weakened. While the global glaciation was in effect, the tectonic activity of our planet did not stop. Volcanoes continued to erupt, adding carbon dioxide to the atmosphere, which gradually began to accumulate again. And here, the reverse process starts to unfold. The more greenhouse gases there were, the higher the temperatures became, the ice could start to melt, the albedo decreased, and this led to further warming. In the end, the Earth could have very well freed itself from this icy trap. What's also interesting is what was happening with life during this time. Life on Earth already existed, but in its simplest forms. It might seem that life should have perished in such conditions. Some believe that it could have retreated to hydrothermal vents in the oceans. There is also an opinion that such a sudden change in conditions actually stimulated evolution and triggered the emergence of more complex organisms. And it is also possible that such a severe glaciation didn't actually occur. As I mentioned, scientists generally agree that there was at least some kind of an ice age at that time, but the details are where disagreements arise. Some argue that the ice was thin in many places, allowing sunlight to penetrate into water, which would have supported photosynthesis reactions. Not all scientists believe that the entire Earth was completely covered in ice. It is possible that there were large areas of open water at the equator. In a more moderate scenario of global glaciation, life could have survived the period in areas with more favorable conditions. Some even argue that the presence of glacial traces in tropical latitudes can be explained not by glaciers forming in the tropics, but by the fact that the Earth had a different axial tilt at that time. This would have placed a climate similar to tropical one into different regions. The tilt of our planet's axis can change over time, but such a scenario would require a more extreme shift in tilt, and there is little evidence to support this theory. And here's a question that might concern many. If this really happened in the past, and we have a fairly clear understanding of how it would have occurred, could it happen again? Well, regular ice ages were not that long ago. The Ice Age ended about 12,000 years ago, and now we are living in the interglacial period within the Quaternary, where cooling periods alternate with warming periods. But these ice ages are nothing compared to the global glaciation we're talking about today. Moreover, the sun is shining several percent brighter now than it did hundreds of millions of years ago, and we shouldn't forget about global warming associated with human activity. Overall, the specific set of conditions and circumstances that could have triggered a Snowball Earth hundreds of millions of years ago is extremely unlikely today, and the sun's luminosity will continue to increase in the future as well. Though it doesn't mean it's entirely impossible. Some catastrophic scenarios still can happen. For example, a collision with a large asteroid or a comet could lift a massive amount of dust into the atmosphere, blocking sunlight, which could lead to global cooling. And of course, the Earth would freeze without the sun. The sun, of course, won't just disappear on its own, but if we really start to fantasize, we can entertain such a scenario. A rogue object enters the solar system. A massive rogue planet, a neutron star, or even a black hole. Such objects could destabilize the solar system, potentially causing the Earth to be ejected from it. Rogue planets do exist, and many of them, if not all, were once part of other planetary systems. The farther the Earth moves from the Sun, the less light it would receive, and it would get colder. Pretty quickly, Earth would turn into a frozen ball. Although it's interesting that the ice cover could act like a sort of a blanket, keeping the ocean depths from freezing for quite some time. Such a scenario is not impossible, though of course is extremely unlikely. While we can't say with 100% certainty that during the Cryogenian Earth was completely frozen and turned into a snowball, there are still plenty of arguments in favor of the idea that an incredible ice age prevailed for millions of years. Thanks for watching. Links to all of the sources are as always down below in the description, and if you enjoyed the video, leave a like, comment and subscribe for more videos in future. Bye!